Hayley Shen from Clarkson.
Okay, am I already on this microphone?
Oh, you need the micro. Oh, you have.
Yeah, I have. I don't know whether it's turned on. Okay, I thank John for inviting me to come back here because I gave this talk in the second workshop, and this opportunity will offer me another chance to talk with a different group of people. What I want to talk about today is wave propagation through ice covers, and this has been worked in the past 4 years with field components, but before that I have just worked on this off and on, and it was because Arctic is melting, so all of a sudden this becomes a very important problem. So there's a very concentrated effort of a large group of people, and as you will see that we will be using lots of data to calibrate and validate the model. This problem is a layered material, wave propagation through a layered material. It's not an isolated problem. There are other problems, physical problems in our Earth system that is very similar, also has very similar mathematical structure, like porous wave barrier. Ocean propagating through this will be damped, and ocean and the mud interaction. This is important in the coastal zone, and ocean and the earth crust. This is the earthquake interaction with the water body. So only very recently I started to compare those systems with our ocean and wave, ice and wave systems, and I found lots of similarities there, but haven't gotten very deep into these different fields. The reason that we have to study this problem is because Arctic's melting, so provided opportunities for navigation to go through. And yesterday we also heard another talk mentioned about this economic driver. There are other drivers which allows us to investigate why is it important wave and ice interaction in this region. Now, if we turn that around so that we have this map and this map, same orientation. If we want to navigate in the ocean, we need to know what is the climate there, including the wind and wave. So we have to have a good wave model. Although Arctic is melting, it's not ice-free, so we have ice. And actually it's more hazardous because the ice can go in and out and move very quickly now that it doesn't cover the whole Arctic, so it's freer to move around. So it becomes more important to be able to have a good wave forecast model. Here's a wave forecast model, but it only works for the open ocean. We don't know what is happening in the ice. And if we want to travel through the ice, in which we cannot guarantee, even we know there's less ice, we cannot guarantee that today we go out, there is no ice here, but tomorrow there might be. So we have to be able to expand the wave model to be able to cover the ice-covered area. The wave model follows some mathematical equations, and this is the wave energy per unit spectrum. In what direction? The wave has directions all over the place, and it can have a spread of wave directions, so each direction has a certain amount of energy at some location and time. So this quantity is advecting by the group velocity. Group velocity is a measure of how energy transport, which is dependent on the frequency and the wavelength. And this energy can also grow if we have wind, or decay if we have white capping the wave breaks. So we have source terms even in the open ocean. With ice, we have additional damping term. And not alone that this will cause damping, it may also affect these terms. If they are modeled in the open water, they might change. But so far, nobody has looked into that part yet. So we are focusing on how waves damp energy in the ice and how does wave speed change. we can encapsulate those two quantities together in the real part of a wave number and the imaginary part of wave number. This is related to the wavelength. 2 pi over this quantity is wavelength. This is related to the energy damping per unit length. Now, we sit in our office and think about why would this depend on the ice cover. Well, you can imagine that wave propagation through different medium will be different. It will change its speed. We are familiar with those kind of phenomenon. So we know that this quantity is going to be a function of frequency. It's going to be a function of the ice property. So now the question is, what kind of ice property does that depend on? So we don't know that. And by the way, ice is not a uniform material with constant property everywhere. And we are particularly interested in this type of ice cover because imagine that the ship will not try to go through very packed 100% ice covered region with lots of ridges and so on. It likes to travel where the ice is less, so it's easier to travel through. So we are probably going to face this kind of situation like the most urgent problem to solve, or this kind of situation. By the way, this kind of situation is probably more often during the spring to summer melt, although actually this picture was taken in the fall, but it was still above freezing, so you see the remnants of broken up ice pieces with some new growth in between. If it's really summer, then you have open water in between. So we have this type of ice cover, and we have this is fall, newly growth from open water, you see this type of ice. So we are more interested in this type of ice. How do they interact with wave? And so because I'm here with a fracture workshop, so I needed to think about why is that problem relevant to the fracture. So this picture is actually very revealing. This is a SSMI ice concentration map. Darker color represents higher ice concentration in 2012. And you notice that there is only a 5-day difference between those two maps. It changes a lot. Of course, it was due to a big wave event, storm. So it took away a lot of ice near the edge. Of course, then it shows how important it is in order to understand how wave interacts with ice in the ice edge. But look at the central part. It also changed a lot. And I would think that this must have to do with the strength of the ice cover changed during this 5-day period, together maybe with the environmental driving forces increased. So things start to move around a lot, not only along the edge, but also interior. So in 2014 and 15, we tried to use satellite images to understand how ice surface texture changes with wave and wind. And the texture that we were interested in was this lead spacing. And you can see that as, oops. Yeah, what is the matter? Maybe I need to touch this all the time. Okay, so I will try to do that. And, okay, so we see the spacing between the leads. And as this season goes on, several days later, and this is also more sudden, you see the leads developed into this irregular shapes. So evolves and gradually becomes flows and free floating like the picture that we saw earlier. So we try to use those pictures to study the spacing and correlate that with the wave. So here we see the close-up. You can see frozen ice pieces among the thinner ice, and you see cracks forming. So we use image analysis to define a linear approximation of these lines and measure the distance between And we find that there is a definite positive correlation between the lead spacing and the wavelength. So it means that fracture in an ice cover is probably impacted by the wave action. So we need to know how wave propagates through ice cover to know what kind of wave will arrive at this interior place in order to create those fractures.
How do you calculate the wavelength in this case?
The wavelength is from the simulation that the model that I showed is WaveWatch 3. So we use the WaveWatch 3 as a model to predict what's the wavelength at the ice edge. These wavelengths are the ice edge wavelengths. Not in here, we don't have any real good data of what's the wavelength there. So we just correlate lead spacing with the incident wavelength. Okay, so in order to have a good feeling of, or a better understanding of how ice affects wave, I think it doesn't hurt to review what is the wave propagation characteristics, or what could affect that. So recognizing that not all of us remember what's the wave dispersion from our undergraduate study, I will quickly review that. If we have open water, we start with irrotational velocity field. So we have a potential describing the velocity components in the horizontal and the vertical direction. And because we have this irrotational flow field, you can take this derivative with z, derivative with x, they are equal to each other. This is an important relation that will be used to simplify the equation of motion. So the equation of motion is the familiar Euler's equation. And this is for the u direction and for the v direction. And remember that du dz from the previous slide, this is the same as dw dx. So we can combine those two terms to form that one. And dw dx is equal to du dz, so we can combine these two terms to form that one. So actually those two equations become very similar because you remember that potential flow says this can be represented by gradient of the velocity potential. So this becomes a phi, this becomes a phi. So the two equations can be combined. So we have the first equation, x direction and the v direction like this. And if we integrate with respect to x, we get this term. Integrate with respect to z, we get this term. So both of those equations will be the same. And we can arbitrarily set this constant equals to 0 without affecting anything because you can put that into this phi. Okay, and then we are looking for a periodic solution because we are solving for waves. So we have periodic in z, periodic in x and t. And then we put this phi into the equation and then use the surface condition. On the surface, the vertical motion of this profile has to have a velocity equals to the velocity of the water. So velocity of the water from periodicity, we have this relation. And therefore, the surface elevation and velocity potentials are related with each other like so. And then the dynamic condition, the one that we saw earlier, can be simplified into this form because your eta is what is the best into this one? Okay. So your eta is substituted by k over sigma times phi. And if we drop the nonlinear terms and set the pressure on the free surface equals to 0, we don't have those two terms. And this whole thing simplifies to this term, which is our final dispersion relation once we cancel this phi. So for open water, we have frequency of the wave will be related to the wave number. Long wave in period will also have, long wave means frequency is, period is long. period long, frequency is small. The wave number will be small, wavelength will be high. So long wave will be long period wave will also be long wavelength. So there is a direct relationship between frequency and the wave number. But this is all dependent on dropping that term. So this is only a linear wave result. We drop nonlinear terms. And it also depends on there is no pressure free surface on the top. So now imagine that it's not free surface. We have ice cover on top. Then this pressure is no longer equal to 0. It will be closely related to the material property of this layer on top. So we drop that term, no longer true. Historically, there have been several models which has been developed by people who want to understand how ice affects the wave propagation. So you can see that this is very long time ago. In this model, we imagine that we have an elastic sheet. So with the elastic sheet, we have a constitutive law which is only related to the Young's modulus of Poisson's ratio. Combined into this flexural rigidity, this equation changed into this one. This was developed with this kind of ice cover in mind. We have a continuous ice cover, even though there are lots of irregularities, ridges, and so on. We imagine that first order approximation, this whole thing is elastic. So that model was not meant to be used for something which is more like this kind of situation. You have individual ice flows on top of the water surface. And if they are not interacting, which is key, if they are not interacting, then all they do is store energy when the wave rises and then release the energy into the kinetic energy and back and forth. Because their buoyancy is not the same as water, so the storage and the release period is different. So they will change the dispersion relation. The governing equation is like this. So ignore that one. This is for open water. We have this one instead. And that is more or less within this kind of ice cover in mind, each non-interacting floating pieces. Quite different from the previous mental picture of what is ice cover. And then this year we have another different model. This one is thinking this is just a slurry. You have viscous material. Now things become very complicated. When you have a viscous material, this is no longer irrotational flow. So you cannot just say the velocity field for this material is a potential flow only. You have to put in a string function. So mathematics becomes complicated but still manageable, and you get different dispersion relation. And that model was supposedly applied for this type of material where you have very small ice pieces mixed with fragile ice, and you have a thick layer of the stuff. So conceptually, this is like a slurry. However, the trouble is all of those ice covers exist in the ocean, and there is no single model that's going to be able to describe all of those. So what I will show next is a movie of a voyage from top of the Sakhalin Island to here. And you will see how ice cover changes from here to here. And this was taken from a museum in Manbaichu, and it's an amazing museum. There's a long way from parking lot to the entrance of the museum. On the wall, concrete wall, they put in different ice stages by doing some concrete art. So the display is all the way from parking lot to everywhere in the museum. Okay, so here you see that we have frazzle, and the scientists picked up the material and show us the texture. And you can see small pancakes are starting to form, and you have waves becoming more and more regular, those ripples disappear, the ripples that you saw over here disappears, and they become larger and larger, and they seem to go forever to the end of the horizon. But if you go several more kilometers, you see, oh, they have now congealed into similar size of pancakes, and the pancakes will keep growing, and they become elongated shapes, and the scientists picked up one pancake and shine it in the sun, and you can still see the small, very tiny circular structures that formed this pancake. So we have this freezing process going on as the ice and the wave interact more and more. You have longer and longer waves, so the separation forces between two small pancakes drop, and therefore they can freeze together, and now you see longer ones. Okay, so all of these ice shapes exist in nature. Yeah. So the previous models that we have discussed, the open water has this dispersion relation. It's just non-dimensional, so you can forget about what details. Frequency wave number relation for open water is very simple. For individual flows floating on top with no interaction, you have this one, and it becomes more and more complicated. And the other thing to notice that is, in this solution, there is no complex solution. It's real, so there's no damping. Same thing here, only real solution, only real solution. Only this one will give you damping because you have a complex equation here. So you have both real number, Kr, and complex number. Okay, so we have to find a way to model all of these different types of ice. And in 2001, we analyzed the data in Antarctica and find out typical flow size versus distance into the ice edge grows exponentially. So it goes from here to here to here to here. So we have all these situations. So what do we do? How do we find a simple model which is going to allow us to transition all the way from open water to the interior of the Arctic? Right. So our dream is that one day we will be able to look at the satellite pictures to I touch this, it just keeps going to different okay. Okay. Thank you. Alright, we have waves generated here, and it propagates into this ice cover, and it will change because material changes. So probably we'll see different dispersion relations everywhere. That's what we imagine. But how are we going to find out what is the dispersion relation at different locations of this ice cover? Without knowing that, we will not be able to predict what is going to be the wave condition anywhere. And then we will not be able to do other applications such as how do we navigate there, what's going to be the wave fracture potential. So first problem is, how are we going to find out how does wave propagate to different kinds of ice covers? So we know that each of the previous models that we saw had a different mental picture of where is the applicability of those models. And we recognize that each of those has some validity, so why don't we combine them? So we try to combine all these models into a viscoelastic layer material. So this is our mental picture. We have a material which has an unknown viscoelastic property. But because of the elasticity property, it can store energy and release it at the rate of dependent on the elasticity, and therefore changes the wavelength. And it has different viscosity, so it can damp energy at different frequencies according to the proper viscosity. So this appears to be as simple as possible and necessary. So we developed that one based on Keller's model, which was pure elastic. We add in a complex viscosity over here. So we can allow elasticity without changing the mathematical structure. So we solve this system of equations. And the model that we adopted captures the basic physics, which is energy storage and dissipation. And it also can be shown to converge to all the previous mathematical models. So it seems to be, it doesn't give you a different model, it just try to integrate everything together. All right, so here is the mathematical structure. This part is for the top layer. It has its own momentum equation. And this part is for the bottom layer, which is the water. And you have to match the motion and the stress between the two layers in order to make them into a system that agrees with each other. So boundary conditions, if you have inviscid material here, you have no shear stress, but the pressure has to be continuous, and the velocity has to be continuous. So these are the boundary conditions we applied to this system of equations to solve. Unfortunately, the solution is very complicated. If it's open water, this term becomes 1. So you just have the simple one, sigma squared equals to gk as we saw before. It equals to 0 over here. All of these terms drops. But with this viscoelasticity, we have this term and this term, which gave you this structure. And we solve for k, the wave number. If we know sigma, we can solve for k once we know the big assumption. Once we know the viscosity and elasticity of the ice cover, we try to describe with this model. Okay, so this shows that this system of dispersion relations can converge to mass loading, that model thin elastic plate under these limiting conditions. Just prove that this is not a new model, it's just integral of the previous models. All right, so how are we going to use this model to simulate wave propagation through this? We cannot derive the elasticity and the viscosity. So I will show you how eventually we did that. We used the calibration. First, because this is a math workshop, so I talk a little bit about the math of this model. This model, unfortunately, has infinite many solutions, many roots. But there are only several of those roots that are actually propagating with not so big damping so it can be observed. And these are the roots that are close to the 0, 0, close to the open water. So they are the physically important ones. So we try to understand what they are. And we did understand, we found that there's a flexural gravity wave, and there is a pressure wave, and there is a shear wave, and those are Rayleigh wave solutions. But the trouble is, okay, so we say these are high damping because your Ki value is high. So let's just forget about those. And we can also prove that shear wave has no energy. So the only left important roots are those two roots. And we plot those two roots as a function of the elasticity of the ice cover. What we find is this root, root 1, which is a flexural gravity wave. happily march along this line for small elasticity, but suddenly drops. Well, the other route, which is this crosses, the second route here, that follows this line, which was what the first route likes to be approaching. It follows that one, and suddenly when this route drops, this route assumes the role of the previous one. On the map, what happened is this one will close into that one, and this one will move to 0. And when they are almost touching, this one will become a flexural wave, and this one will become the pressure wave and very quickly drops to 0. So we have one route gravity wave becomes this one, pressure wave, and one route starts with a pressure wave and becomes gravity wave. We don't understand this, but I found the same thing happened to other layer systems. So we dropped this mathematical problem and said, don't have time to really understand the mathematics. We will focus only on the gravity wave. So for the gravity mode, we have this branch and this branch. This is a real wave number. This is the imaginary, the damping part. The route will follow this way. So for each G and viscosity, elasticity, viscosity, we can solve these behaviors as a function of frequency, as a function of all the parameters. So we will be able to predict how the wave will propagate under this viscoelastic material. But since we don't know how to determine the viscoelastic material from basic physics, therefore, for each of those, the basic physics is probably all different. So what we think is each different ice morphology has some way of determining what is the viscoelastic property it should have. But the gray thing means that we don't know that. But each morphology, this type of ice cover, if we can put instruments there to directly measure the wave property, then we can associate this wave property with the dispersion relation to calculate what's the GNU for each type of ice covers. So if we can measure what is this K, we can then use the dispersion relation to inversely determine its property. This is like we don't know the viscosity of water, we just measure it and there we go. How do we measure that? We can assume that if you have a constant shear, you have the shear rate related to, so you have to have first a constitutive relation. So here we have a constitutive relation that gave the dispersion relation. We use the measured outcome to inversely determine those. So what we need is data. We need to find out each of those ice cover, what kind of properties we have. So in 2015, this group of us had the opportunity to spend 7 weeks in the Arctic Ocean, and the group deployed 3 different types of ice buoys. I should point 1 type, 2 type, this is hollow, this instrument box will go into there and put into the ocean. There's a 3rd one over here, and this is the retrieval process. You can imagine how difficult it is to do this. It's very different from ice station. You know where things are, and you put your camp right there, so you can take care of that. Buoys, you drop it into the ocean, and then you leave. And you leave, you take 100 kilometers away, and you have to come back and look for this tiny thing in the big ocean. But it was done, and we had 4 experiments, some over 3 days and some just over 2 days. And each time we deployed a number of buoys. And we had different conditions, wave condition and the wind condition and wave speed and so on. So we try to capture as many different events as we can. And this is the trip trajectory. This is end of the trip ice edge. We started with ice edge over here. 7 weeks later, we had ice edge over here. So our route was going this way, and this way. And we had an experiment here, here, and here. Okay, once you put buoys in the ocean, you have two buoys, and you can measure the power spectrum density, and you can separate energy of each frequency at those two locations. And you take the log between those two locations and divide it by the distance of the two, you can get a damping coefficient. And the distance is the wave direction distance, so you have to measure the distance with x and the wave direction and find out the angle difference between the two. So we did all that and took all the buoy pairs that we can have. For this experiment, we had over 500 buoy pairs. And this is the damping curve. As you can see, it scatters 2 orders magnitude. But that's reality. With theoretician, this is very uncomfortable. And then this one, we had only a few data sets. This was a very variable ice condition experiment. And this one, we had about 100 cases, and this one, we had about 300 cases. So we use all these to do this inversion. And you can also see the ice condition for each one is quite different. This is within the same experiment at different time and location. The ice varied. This is also same experiment, different location time. Same experiment, different location. So it's very difficult to control the ice condition, so you have always the constant. That's why we had all that scatter. Okay, so we did this inversion method, and we found out for this wave experiment, the G, the elastic and the viscous coefficient clustered over here or here. There are two groups, possibly due to the different conditions. We tried to look at all possibilities, but we haven't found a real clear signature. Why G and nu differ that much? But actually, it doesn't really matter because this G value is so low, it can be just approximately equal to 0. This G is also very low. You might wonder what kind of material can have elasticity 10 to the 4th Pascal. I looked online. Only thing that I can find is biological tissue, so like your brain. And for this one, you have similar situation. You have two groups. This is very small, so we don't care about that one. We have approximately the same G value, and same thing over here. So it seems like in order to describe what we saw by using this simplest viscoelastic model, we need to put in elasticity and the viscosity at these values. So does that work? We saved one experiment, so we only used 3 here. We saved one experiment to do the validation. Here we did a calibration. So here is the comparison. So these are the curves that we directly measured. These are the curves that we used the best fit G and nu to recalculate. Each color represents the G and nu values from a different experiment. We had those 3 experiments, so different G and nu values, we use them to recalculate the spectral damping versus frequency. What jumps to you is the bulk of the match is near the central frequency where most of the energy, I didn't show what's the energy, but this is where the wave energy is maximum. While the low frequency and high frequency part, we have big discrepancy.
Hayley?
Yeah.
They look so flat to me. Shouldn't there be a... Why
is it flat? Yeah, this is more flat than the other two. I don't know.
Because the other measurements you showed seem to have some slope.
Yeah. This one, this attenuation, I think to get into that will probably even make things more complicated, but I still have to say that. This attenuation is the parent attenuation. So it actually does not measure what's the ice effect. It measures all the other source effects all combined. But because this is the low frequency, so I still think the other, like wind, cannot put in that much energy in the low frequency part. I don't know why this is so high, but that's data.
But it doesn't match the other data you showed. The other data appeared to have a quite clear slope.
The other data is quite slow. This one, this experiment is a troublesome experiment. That's why we didn't use it for calibration.
Okay.
Lots of the pairs didn't pass those filter tests, such as you cannot have an increasing energy with frequency, and you cannot have missing energy in some big band. So those were deleted, and that's why we only end up with 7 pairs over here.
Okay.
But anyway, that's the only thing we have to compare with. So we still kept this one. But I would say in general, although this is the worst case scenario, the other cases that we didn't show over here also has the same type of discrepancy, that is at low frequency, the data is much higher than the theoretical model. So that shows there's something wrong with the model. Something is still missing. Okay, so in conclusion, we need to have a wave model that can apply to large variety of ice covers. In order to do the next step for fracture mechanics, you need to know what is the wave condition at the central ice pack, so you can predict whether you will have a crack there. So if you don't know what is the wave at that location, you cannot do that job. But in order to do that job, we have to know how to describe the property of an ice cover. And it doesn't seem like we have a very good physical model that could be applied at this moment. This is probably the best we can do at the moment, and the discrepancy in the comparison should stimulate us to look for how to improve those models. But I still feel nature is so complicated, so I don't know. Maybe we can use the wave forecast as our role model to see what is the road that lie ahead. Because you think about wave model now can give you pretty good prediction. It will tell you tomorrow it's going to be 70% shower, but it cannot tell you tomorrow it's going to shower, or it's going to shower in Cambridge but not in Canterbury. So accuracy of those models, including the ice wave model, probably will never be precise, but we just try to be able to go into as good as we can by incorporating the correct physics into it. Thank you.
Question?
When you are saying the fundamental theory is still missing, is it means something missing, or what we are doing is completely wrong?
We are not doing enough. I think what we are doing is right, but we don't know enough about what to do right now. So we are still looking for what's missing and what should we do to improve. And we sit here to imagine what is ice like, and you have very complicated models which can describe polymer materials, and you have coefficients, that 35 coefficients that we know we probably will never be able to use that kind of model for ice. So we try to come up with simple models that seems to agree with our intuition. And then we solve it, and then we compare and make observation to see what's wrong. So that's just the way research goes, right? We don't know what is right, so we keep doing it.
I'm wondering, how do you know the direction of the incoming waves? I think you said you knew that azimuth.
Yeah, that is those buoy people can tell you very well, because they put 6 degrees of freedom sensors, so they can resolve what is the direction of the wave. Wave actually is not one direction, it actually has a spread. So they can find out the strength of the signal in each direction and do a power spectrum density, directional power spectrum density. Yeah, Steve?
Excuse me, when you say that this model is viscoelastic, You mean that you have one layer of viscous and one layer and plate of elastic wood, yes?
No.
But it's not
The
maximum
material
area.
itself is viscous. I didn't stress that. So it's right here. This material here has this constitutive law.
Okay, and relaxation time.
Relaxation time is represented by this viscosity over. This is a void, Kelvin void model. So you can solve the relaxation time. I don't have it in my head, but.
Yeah, but for example, I had actually a related question because you invert the two parameters,
Yeah.
I mean the shear modulus and the viscosity. So, what would be the corresponding relaxation time from the data you get from your inversion method?
Okay, because before we do the inversion, we don't know what viscosity we are getting. So we don't know a priori what is the relaxation time.
No, but when you finally you have a slide where you have result of your inversion,
Yeah.
and you have that result for viscosity and shear modulus.
Oh, you mean I can then calculate?
I mean, translate that in terms of relaxation time, no? For those two groups, for example.
Yeah. So I needed to have that relaxation time in my head. I think it's V over G sigma, something proportional. But why is
It's the
why is
ratio
that
of-
important?
it should be the ratio of
Yeah.
of the two parameters,
V
so-
over G sigma. V over G sigma is something like that because that's dimensionless, right? V over G sigma. No, V sigma over
Oh,
G.
it's a Kelvin void.
V sigma over G seems like that dimension is right. But why is that important?
No, I mean, just to,
Oh,
I mean, I would have been happy to have some numbers to know how long it takes for your viscoelastic material to relax elastic stresses. That's it. From this number.
yeah, you can calculate. So
Yeah.
okay. But again, I ask, why should we know that?
For example, because I think that this could be a way to have some idea of some mesoscale rheology for sea ice, broken sea ice, as you have seen some picture. And so in this case, it would be interesting to use those numbers and to have some ideas.
Okay, I'll talk to you later.
Okay.
Are you thinking about ice dynamics transport? Are you thinking about applying this to the ice dynamics, the transport?
Oh yeah.
Because you're talking about relaxation of stress.
And so on, yeah, for some.
Yeah, I mean, you chose just scalar values for G and nu based on these, but here, in some cases, for example, nu varies over, like, what is it, 4 orders of magnitude?
Yeah, this nu is from 10 to the 0 to 10 to the 2, so it's,
Yeah, but there it's between -2 to
yeah, this is
2.
from -2 to 2, yes.
But you chose a single value.
Yeah, choose a single value.
I mean, so the question is whether this variation of several orders of magnitude could be significant.
Yeah, so maybe we'll cover this over here.
So that's the question, basically.
Yeah, right, so we only use the mean value, that's true.
Yeah, but that may, so if you, I mean, that would imply maybe more complications, because if these variables become non-uniform, so
Yeah,
you start to get non-linear terms.
yeah, I think that's why I feel maybe we can just use weather as a role model. We should not ever hope that this is the number, we go put our buoys, we should get that number. There will be an error bar. But I don't know, that's just so far, I guess. But we are looking for the trend. So if the trend is wrong, then something is missing. The exact number is probably it's easier to accept, that we should not expect to have the solution. But the trend has to match.
Yeah, was there any attempt to measure the dispersion relation with two closed buoys, or the buoys were basically measuring the attenuation only?
There's a marine radar also on the ship.
Okay.
And there's also another method using the pitch roll of the buoy, the gradient or the slope of the surface to measure the wavelength. So in this paper, there are also data reported by, in this paper, there are also data reported by 2 other scientists. One used marine radar, the other used the buoy tilt and pitch to determine the wavelength. And we also use that. But for the type of ice we have encountered, there was no change, only 1% change of the wavelength from the open water. So we ignore it. But we believe that if you go to the pack ice, there will be big changes. And we didn't go in there, so we don't know.
I think in this, Stasha was saying that we've done poorly in modelling, and part of that is that we haven't had these measurements until now, right? So we've all been modelling in a vacuum. But when I read the paper by Keller, it clearly states that the attenuation goes as the frequency to the power of 7. So, which fits with those very steep curves that you showed, but none of the data matches to that. None of the data has an attenuation that matches to that power of 7. If I put that on a log-log plot, the slope would be 7 if it follows from Keller, which I'm pretty sure your model does. So it seems to me that this model probably isn't the model to use, and that we maybe need to look for. I think the idea of using dispersion equations is great, and of course in the viscous layer it's all sounded very sensible but now that we have these measurements, we don't observe this power of 7 dependence. So maybe we need to accept that this model that Keller wrote down that you've worked on isn't actually the one to use in this particular case.
I agree. And actually, we tried the other model by Liu and Moller-Christensen. Their viscosity came from the eddies in the water body. So their model predicted this slope, or this part of the slope, from -7 to -3. We talked about that yesterday.
Yeah.
So that made me think that maybe eddy viscosity is very important to bring the model. So that could be the next thing. And in this cruise, there are also some measurements about the eddy viscosity in the ocean. And it showed that under the ice cover, you cannot assume that's equal to 0. So there is some eddy viscosity there. Whether that's sufficient to change the slope, I don't know. But it looks like our next model would be viscoelastic layer with the eddy viscosity on the bottom. So that incorporates damping both from the second layer and the top layer. We recognize that the top layer must have viscosity because you see the interaction, you see the slurry. So there must be viscosity on the top layer, but that may not be sufficient.
But I wonder I just question whether Keller wrote down his version of the viscosity is based on the sliding of these layers. It may just be a compression effect, or there's other ways of incorporating a viscous damping that don't rely on such high derivatives, and therefore you get a lower power of. I don't know. It's an interesting point.
Yeah, I don't know. I think the viscosity from Liu and Moller-Christensen clearly comes from the water body. It's not coming from the compression of the surface layer.
And then it doesn't depend on the thickness, which is interesting. So does this? So there's another factor here that we can compare. I agree with that. Yes.
And Steve, you had a question?
Could you account for the effects of wind during the
Yeah, the wind is, when we did this calculation, we measure the power spectrum here, power spectrum there. And if the wave propagates in this direction, along its way, it's receiving energy, then you cannot directly use the energy here and here to calculate what's the damping due to the ice. So we have to account for the energy input from here to here from the wave, or from the wind, and then modify what is this term, and then do this calculation.
My question is about the dispersion relation of everything. So could you show the thickness of that ice in this dispersion relation, where it is?
Where it is.
Yeah,
Okay.
which is thickness?
Yeah, it's not explicitly written in all these C, K, and SK and alpha. These are hyperbolic functions, sine and cosine, and they are K times H. So
Time H, and
the
H
thickness.
is thickness.
yeah, so they appear in all these terms. They also appear in this term.
My question is about the conditions for this dispersion relation. I assume that this dispersion relation works only for long waves. I mean long compared with the thickness of ice, right? And then that K, little h, as I understand, it's small, right? So if we use that thin layer approximation, floating layer of small thickness, what happens with this relation? Is it getting very simple, or it's almost the same complexity?
We haven't done the perturbation analysis on these terms, assuming H is very small, but we have done this one right here. Thin elastic plate theory. If we let KH very small, so I'll correct myself, if this term is very small, and if this term is much smaller than this one, so here you can see the H effect, so this term will be approaching 0. And this term, I don't remember the alpha over here.
Yeah, but that dispersion relation, it's exactly dispersion relation for thin elastic plate. So
Yes.
it's well known.
Yes.
But if you add
A higher order term, yeah,
on the top of it,
right.
what's happened is that
I did add this. We allow VE to be. Oh no, this is a pure elastic. So I dropped the new term. Then you can prove it converges to a thin elastic plate. If you don't, if you keep the new over here, it will still converge to this one, but this is a complex number.
Okay.
So it will converge to the Fox and Allen
So
model.
it's Kevin, so-called Kevin-Voigt model of dumping.
Yeah, this
Okay.
This
so
this
that-
whole
okay.
yeah this whole theory is based on this is a very specific viscoelastic model. So you can make that complicated and you probably end
You
up
could
with
try another
yes.
viscoelastic model like Maxwell or
Yeah.
Yes. But we tried to do that, but the mathematics becomes very complicated. Kevin Voigt is one that's most straightforward that you can get a closed form solution.
maybe one last question.
Yeah. You mentioned the possibility of adding eddy viscosity. That would imply that over the open ocean you would have attenuation also.
Yes.
Has any comparison been done for these?
For the open ocean?
Yeah, these dispersion predictions over open ocean.
I really don't know. I don't know. Mike, do you know if anybody used eddy viscosity in open ocean?
No, I think that you need to have that layer there to give it the. There is
But
there is
open
another
ocean also
model.
has eddy.
Yeah, there's another model that Tim Williams used, from the Nansen Center, which is based on this Robinson-Palmer model, which is also another layer model, which gives similar. I think both of them have a constant and have almost the same behavior as the eddy viscosity model, and maybe they're related.
Mm. Yeah, but to answer your question, for open water case, they are most concerned with the white capping, turbulence. You can say the turbulence part is similar to eddy viscosity. So they damp energy that way. They have a turbulence in the upper layer, they have wave breaking on the surface, and that contributes to damping.
Okay, I think we can close the session. Thank you.